In this video, we demonstrate proof of concept 3 of the 6G-Cloud project, implemented on the experimental infrastructure of the National Center for Scientific Research, Demokritos. PoC-3 validates two core pillars of the 6G-Cloud architecture. First, the network digital twin concept is demonstrated as an enabler of safe synthetic data generation and closed-loop AI/ML model training and validation. Second, the network of networks concept is validated end-to-end across the following dimensions: flexible instantiation, placement, and composition of core network functions to create multiple network services on the same hybrid cloud and edge infrastructure. Coexistence of multiple network services under the 6G-Cloud architecture design. Dynamic interconnection of network services driven by AI/ML-detected network conditions. Following the service-oriented 6G-Cloud architecture, our experimental infrastructure is structurally divided into 4 interconnected primary domains. At the top layer resides the Management and Orchestration Framework, MLEF, operating primarily through the Katana NS Manager. This domain handles end-to-end life cycle management and cross-domain orchestration. It effectively translates high-level service intents into actionable deployment configurations, allocating resources across distributed environments. In the center lies the Network of Networks paradigm. This features a unified 3GPP-compliant service-based architecture SBA control plane, housing essential network control functions such as the AMF, SMF, AUSF, and RF. This centralized control plane dynamically manages distributed and isolated user planes. By dedicating specific user plane functions UPFs, it seamlessly bridges public network services with private localized non-public networks NPNs, ensuring strict traffic isolation and quality of service. On the left, the AI/ML framework integrates the network digital twin. This component forms a continuous closed-loop feedback system. It extracts real-time telemetry and state data from the live network infrastructure to build a high-fidelity digital replica. Utilizing this robust data repository, the framework trains advanced machine learning models enabling predictive analytics, proactive resource optimization, and the real-time anomaly detection we demonstrate in our test bed. Finally, serving as the foundational layer is the Cloud Continuum Framework, CCF. The CCF abstracts the underlying physical hardware and network resources, managing the distributed Kubernetes clusters across both edge nodes and centralized data centers. This ensures the scalable, resilient, and automated deployment of these complex 6G functions. This slide illustrates the architecture of a network digital twin within a 6G cloud environment. It highlights a continuous, bidirectional link between the physical Microsoft 5G infrastructure on the left and its digital counterpart on the right. The physical side connects various devices, edge nodes, and cloud resources. Meanwhile, the digital twin utilizes this real-world data across 3 distinct layers: a data repository for information management, an AI-driven engine for modeling and analytics, and a management tier for overall orchestration and visualization. PoC-3 deploys a 2-environment testbed architecture comprising a physical network and its network digital twin, operating in complementary roles. The physical network, built on the Microsoft platform, delivers over-the-air 5G new radio with real hardware UEs and a production-grade 5G core, serving as the operational reference for ground truth telemetry and baseline KPI measurement. The NDT mirrors this infrastructure in a fully software-defined environment, combining Open5GS as the 5G core digital twin with uRansom for RAN and UE emulation, orchestrated via Katana. This NDT enables synthetic dataset generation, safe AI/ML model training, and controlled injection of abnormal traffic patterns without impacting the live network. The AI/ML framework, AI/MLF, is the intelligence layer of the 6G-Cloud architecture, providing model lifecycle management, training, inference, performance monitoring, and retraining as reusable services consumable by any network function. A continuous feedback loop ties the physical network, the NDT, and the AI/MLF together. The NDT ingests live telemetry from the physical network to maintain a synchronized virtual replica, then generates synthetic traffic scenarios, including anomalous conditions that would be unsafe and time-consuming to reproduce on the live infrastructure. These datasets train the AI/MLF models, which are subsequently deployed back to the physical network to drive closed-loop optimization and orchestration decisions. A parallel architecture places the physical network directly alongside its network digital twin. On the physical side, real devices, including standard users generating benign traffic and Raspberry Pis generating high traffic, connect to an Amorsoft 5G core. Mirroring the live environment, the NDT utilizes simulated ransom users and emulated high-traffic devices connected to an open 5Gs core. Traffic from both environments is mirrored through a SPAN port and directed to a central monitoring server. Finally, the captured data is fed into an AI-driven anomaly detection and classification engine, which extracts features to classify the traffic and generate actionable alerts and metrics. This demonstration provides a walkthrough of deploying a modern cellular network core, specifically Open 5Gs, utilizing the Katana NS Manager as the orchestration platform. The tutorial is presented in a split-screen format, offering a clear view of both the Katana web dashboard, open-source Mano (OSM) UI on the left and the command line interface on the right. This dual perspective bridges the gap between high-level network slice management and low-level system execution. The process begins with crucial pre-deployment checks. In the Katana web dashboard, the operator navigates through the package management sections to verify that the fundamental building blocks, specifically the network service packages, are correctly loaded. This vital step ensures that the orchestrator has the exact blueprints it needs to build the complex 5G environment. Once these prerequisites are visually confirmed, the action shifts to the terminal. Here, the operator uses the Katana command line interface to upload necessary configuration files and execute a concise deployment instruction. Instead of manual configuration, this single command instructs the Katana orchestration engine to automatically provision, configure, and connect all the intricate components of the Open 5Gs core, assigning them to the designated virtual infrastructure. Almost immediately, the terminal generates an output signaling that the system has successfully accepted the deployment blueprint and initiated the build sequence. To verify this, the operator switches back to the Katana web dashboard and refreshes the active instances list. The newly requested network service immediately appears on the screen, confirming the transition from a simple text command to an active, running operation. Finally, the demonstration shows how to meticulously track this complex process. Because spinning up a complete 5G core network service involves initiating multiple virtual machines, allocating resources, and configuring internal routing, the operator sets up a continuous, real-time status monitor in the terminal querying the Katana API. This auto-refreshing view allows them to watch the deployment operations progress step by step, ensuring every component initializes correctly until the entire network reaches a fully stable and operational state. In order to illustrate the usefulness of the NDT, we briefly illustrate a live network data anomaly represented as a user data GTPU flooding. Moving to the live monitoring interface, a split-screen terminal tracks the network data flow. Initially, the lower window displays a steady, normal volume of data packets. Suddenly, a script executed in the top window triggers a severe network anomaly. The lower screen immediately fills with a rapid, overwhelming flood of data, visually demonstrating a massive and sudden spike in network volume. Moving to the Amorsoft system, a split-screen terminal tracks the network traffic. Initially, the lower window displays a normal, steady flow of data. Suddenly, a script executed in the top window triggers a severe network anomaly. The Amorsoft interface immediately floods with a rapid, overwhelming stream of data packets, visually demonstrating a massive traffic spike before the system eventually normalizes. Presenting the aggregated GPU flood traffic, this figure compares telemetry throughput from the physical network in blue and the network digital twin in orange. Both curves follow a highly similar trend throughout the experiment, showing that the NDT successfully reproduces the traffic behavior observed in the real network. Minor deviations between the traces reflect small timing differences expected in realistic emulation environments. Overall, the results validate the ability of the NDT to accurately mirror physical network behavior during GPU high-traffic scenarios, supporting realistic traffic analysis and performance evaluation in 5G and 6G environments. Moving on to the network of networks, NON concept, it is a core 6G cloud concept that enables the coexistence and dynamic interconnection of heterogeneous network domains. In this case, a public network and a non-public, private, network on a shared infrastructure. As shown here, both domains are served by Microsoft-based 5G RAN, while the public network runs its core functions in the telco cloud and the private network anchors user plane traffic locally at the NPN edge. Crucially, a shared control plane, spanning AMF, SMF, and NWDF, coordinates both networks, while user plane functions remain strictly separated to preserve data locality and enterprise policy boundaries. In our physical testbed, this architecture is realized using standard servers and Raspberry Pis interconnected across a wide area network, with dedicated edge infrastructure and Microsoft 5G radio access on the private network side. This setup concretely demonstrates how public telecommunication services can dynamically expand into a non-public network domain. The MNEF, realized through the Katana NS, orchestrates this end-to-end. It dynamically configures WAN connectivity, cloud and edge compute resources, and radio and core infrastructure on demand, enabling the telco operator to seamlessly extend its reach into the NPN domain and route private network users through the public infrastructure whenever policy or service conditions require it. PoC-3 validates the network of networks concept across two complementary environments. The physical network, built on the Microsoft RAN platform with physical radio antennas and live edge nodes, runs a free 5G control plane shared across both the public and private domains, with dedicated public and private UPFs ensuring physical traffic isolation and hardware-level routing, all orchestrated through Katana. To support safe AI/ML model training and synthetic dataset generation, an NDT of the NON architecture can be constructed by combining free 5G as the shared control plane with URANSIM for RAN and UE emulation. This fully software-defined replica reproduces the same cross-domain management logic, shared control plane procedures, and dual UPF traffic separation, providing an isolated sandbox where non-interaction scenarios, load conditions, and anomalous traffic patterns can be generated at scale without impacting the live network. This demonstration showcases dynamic traffic steering across a network of networks environment, where a shared free 5G control plane simultaneously serves both a public network and a non-public private network through dedicated UPF instances. It is shown how traffic from the private data network, private UPF, can flow upon a decision from the operator through the public data network, public UPF. The screen is divided into 4 labeled terminals. On the top right we see the public UPF terminal, and on the bottom right we see the private UPF terminal. Both UPFs run a live Shark packet capture on the GTP interface. On the bottom left we see the free 5G control UI, and on the top left we see the Grafana dashboard of the traffic passing from both the private and public UPFs. The objective is to demonstrate live, policy-driven re-anchoring of user plane traffic across the public-private boundary. Initially, traffic is initiated in the private network, and on the bottom right panel the private UPF terminal shows an active stream of GTP encapsulated data traffic, confirming that user plane traffic is correctly anchored at the NPN edge under normal operation. The public UPF is initially idle and awaiting traffic. In the Grafana panel, with yellow line we observe the data throughput of traffic flowing through the private UPF. In the control UI panel, the on-screen label, steering from private to public UPF, confirms the moment of transition where the operator executes the steering script directly against the free 5G control plane, injecting updated routing rules that redirect NPN user traffic away from the private UPF and toward the public UPF, simulating a telco operator dynamically extending its infrastructure to service users within the NPN coverage area without any service interruption or system restart. The impact is immediately visible. Traffic ceases on the private UPF interface and reappears on the public UPF, with GTP encapsulated data traffic now streaming through the public domain UPF. In the Grafana panel, with green line we observe the data throughput of traffic flowing through the public UPF, while the yellow line drops to 0 due to traffic not flowing through the private UPF. This confirms the moment of transition, validating the responsiveness and stability of the cross-domain steering mechanism across the NON environment. Within the 6G Cloud project, this steering capability will be further elevated. The decision to redirect traffic across one or multiple UPFs will no longer be manually triggered, but driven by insights generated from the network digital twin and analyzed by the AI/ML framework, closing the loop between synthetic data generation, intelligent inference, and real-time network control. Finally, PoC-3 defines 6 key performance indicators to quantify the gains delivered by the 6G Cloud architecture across orchestration, AI/ML efficiency, and system performance. KPI 2 – System capacity gain through non-cross-network coordination. KPI 5 – AI/ML model development and deployment time reduction. KPI 6 – Data processing efficiency in AI/ML workflows. KPI 8 – Network service customization time. KPI 9 – Service orchestration efficiency via digital twin insights. KPI 10 – System performance improvement using AI-driven functions.